So a cell membrane separates two equally sized compartments. The membrane is freely permeable to water, sodium chloride, while mannitol cannot pass through the membrane. The setup is constructed so that compartment 1 and 2 cannot change volume and the temperature is 293 Kelvin. And so here we have 3 separate experiments, and for each one we have a couple of questions we need to do. So let's start off by looking at experiment A. At T0, so at time 0, 10 millimoles of mannitol and 5 millimoles of sodium chloride are added to compartment 1. Simultaneously, sodium chloride is added to compartment 2, so the sodium chloride concentration here is 10 millimoles, right? So 10 millimoles sodium and chloride, each giving you, or together, coming together, giving you 10 millimoles of sodium chloride concentration. So let's describe the movements of the substances towards equilibrium. Now let's start off by looking at sodium here, right? The concentration is higher in compartment or room 2 in comparison to room 1, so it will go from room 2 to room 1. And similarly, the same thing with chloride. They will go from high to low concentration, right? High to low concentration, therefore, they will move, the uniflux of sodium chloride will move to room 1. And at equilibrium, it will be 7.5 millimoles of sodium in room 1 and chloride in room 1, and the same for room 2. Now mannitol cannot move through this membrane here. Mannitol is impermeable for the membrane. So what we have to do here is look at the water instead. Right, remember water always, when we're talking about osmosis, water will always move from low osmolarity to high osmolarity. Right. So in this case, where is the low osmolarity? Well, it is in room 2 here, right? And therefore, it will go from low osmolarity to high osmolarity from room 2 to room 1, right? So water will move this direction, room 2 to room 1, and will induce hydrostatic pressure because the volume cannot change. Now, what is the hydrostatic pressure difference at equilibrium? Now, remember that at equilibrium, I want you to remember that the osmotic pressure difference is the same as the hydrostatic pressure difference. And so we can utilize the osmotic pressure difference to calculate, and that will give you the hydrostatic pressure difference. So this is the formula we're working with, right? Of course, R is the gas constant, which is fixed, and temperature is 293 Kelvin, right? So we just need to calculate the concentration difference here. Now, concentration in room 1 is, of course, firstly for mannitol 10 millimoles. Then, because at equilibrium, it is 7.5 sodium and 7.5 for chloride. Then concentration 1 here for room 2 is 7.5 for sodium, 7.5 millimoles of chloride, and therefore we can calculate it to be 0.241 atmospheres of pressure. This is the hydrostatic pressure at equilibrium. Now they want us to calculate the membrane potential at equilibrium. Remember that the equilibrium potential for both sodium and chloride is 0 because they are both in equilibrium. And mannitol is not taken into account because it's not charged. Therefore, the membrane potential at equilibrium is 0, right? Because sodium and chloride is both at equilibrium. We don't take mannitol into account. Now let's get right to experiment B here. We have 1 millimoles of protein added to compartment 1 at T0. The protein has 9 negative charges, which are neutralized with sodium. Simultaneous sodium chloride is added to compartment 2 here, so that sodium chloride concentration is 9 millimoles. Now let's describe the movements of the substances towards equilibrium. And since we have a charged protein that the membrane is impermeable to and the volume cannot be changed, the ions will move to what we call a Donan equilibrium. So this is an equilibrium where the ion concentrations on either side of this membrane is static, right? And the Donan distribution coefficient for two monovalent ions can be described via this, right? So sodium So chloride is not in equilibrium, right? It is not in equilibrium, right? As you see here, we only have 9 millimoles in room 2. We have nothing in room 1. So we can say X will move into compartment 1, right? X, compartment 1, and in room 2 we have 9 minus X. And then for sodium, due to the principle of electron neutrality, we'll have in room 1 9 plus X, and in room 2 9 minus X, right? 9 plus X, 9 minus X. And then we can use this formula here, right? And we see that X is 3, right? Which we can insert once again here and see the respective concentrations at equilibrium. So in room 1, chloride is 3 millimoles. In room 2, it is 9 minus 3, it is 6 millimoles. For sodium, it is 9 plus 3 in room 1, and in room 2, it is 9 minus 3, so 6 millimoles. Now they want you to calculate the membrane potential at equilibrium. Now remember, at equilibrium, the equilibrium potential, so the Nernst potential, equals the membrane potential. So we can utilize Nernst equation right here. The gas constant is given, the temperature is given, the ion valence for sodium is of course 1, Faraday's constant is here, and then the concentration for sodium we've just calculated to be in room 1 12 millimoles, and here 6 millimoles. So the membrane potential is given to minus 17.49 millivolts. And what is the hydrostatic pressure difference at equilibrium? I've just talked about it, but at equilibrium the hydrostatic pressure difference is the same as the osmotic pressure difference, so we can use this formula right here. And you'll calculate that at equilibrium the hydrostatic pressure is given to 0.096 atmospheres of pressure. Now let's do see here quickly. So after equilibrium is reached in experiment B, an ion pump is inserted into the membrane, actively transporting sodium from compartment 1 to 2. When steady state is reached, the concentration of sodium in compartment 2 has become 7 millimoles. What is the new chloride concentrations in the two compartments? So after equilibrium is reached in experiment B, sodium will be transported from compartment 1 to 2, resulting in 7 millimoles sodium in compartment 2. And due to the principle of electron neutrality, there will be 7 millimoles of chloride in compartment 2. And therefore, additionally, we know there was previously 9 millimoles, so 2 millimoles will be transported to compartment 1, right? Because previously we had 9, now we have 7. So in compartment 1 we have 2 millimoles of chloride, and compartment 2 we have 7 millimoles. Now what is the membrane potential at equilibrium? The Nernst potential is the same as the membrane potential. So we just insert our values right here and calculate that it is minus 0.031 volts for chloride. Right. Now what is the Nernst potential when we take sodium into account? Well, we can use the same formula here. Of course, the ion valence is now changed, and these two concentrations are also changed, right? Here we know it must be 11, right, and 7 millimoles respectively for the two compartments when we're talking about sodium, right? So that comes to give us the membrane potential of minus 11.4 millivolts. Now what is the hydrostatic pressure difference? Of course, we can use this formula. I've talked about it again. We know with the hydrostatic pressure difference is the same as the osmotic pressure difference at equilibrium, and so we can use this formula. We insert our values and we'll see that there are the hydrostatic pressure difference is 0. So in other words, there are an equal number of osmotically active particles on each side. This is what you see right here. So this gives us 0, and 0 times anything will give you 0. Therefore, no hydrostatic pressure difference.